Okay, so in the last video, we were talking about local maximums and minimums. So now we're going to talk about absolute maximums and minimums, right? And so the big difference is that now you don't have to say something is the largest value nearby. It's the largest value over the whole domain, right? That's your nearby is now everywhere, right? But let's remember back from single variable functions. There's not always an absolute max or min, right? So for example, if I had the function, let's say y equals the tangent of x on the domain negative pi over 2, oops, it's not defined there, so we can't include the endpoints, which is the whole point of why I'm doing this, on the domain negative pi over 2 to pi over 2, right? The graph looks something like it's got asymptotes at the ends of this domain. So that's a pretty crummy graph, but you get the idea, right? You should remember what tangent looks like. And so you don't have an absolute maximum or a minimum, right? There's, for any value you try to pick as the minimum, you can always get further below it, negative, by getting closer and closer to the asymptote. Same thing in the positive direction. On the other hand, if we decided to change the domain, if I limited this to something like negative pi over 4 to pi over 4, right? So now all of a sudden, I'm shutting my graph off here and here. So now this graph would just be this red section. Now, of course, it has absolute maximum minimums because I've closed the domain, right? And that was a big thing in that version of calculus when we dealt with single variable functions, that you had this closed interval method, that on a closed interval, there was always a maximum or minimum as long as your function was continuous, right? So you might have a function that looks something like this, let's say, where you've got this closed interval. And if you remember the way, the idea when we looked for those absolute maximum minimums was the only way, as long, again, remember the function had to be continuous, the only places the maximum and minimum, absolute maximum and minimum could be was either at critical values, the places where our derivatives were non-existent or zero, right, that I've drawn these horizontal tangent lines at, or at the endpoints. And in this little sketch I've drawn, we'd have an absolute maximum up here at one of the critical values and an absolute minimum here at the endpoint. And those were, it had to be at one of those 2 points as long as we had continuous function on a closed interval. We're going to develop a very similar idea here, but we have to be a little bit more careful because as we've added an extra variable, things get more confusing, okay? So instead of closed intervals, we need to talk about closed sets, okay? So a closed set, let's just start with the definition and then we'll see what this means. The definition we'll use is just a set that contains all of its boundary points. Okay. What is a boundary point? So a point is a boundary point of a set if any disk centered at that point contains points in the set and not in the set. So there's a lot going on here, but it works out to be pretty simple. Let's look at 2 different sets. Let's start with the set x squared plus y squared is less than 1. I'm just looking in the xy plane, right? Because we're talking about domains of our functions right now. right? For closed intervals, you're talking about intervals of the domain. So what is this set? Well, it is a unit circle. Sorry, let me not do it the way I was about to do it. Let's draw. No, I'm going to draw it by hand. So this set is the set of points closer to the origin than 1 unit. Right? If x squared plus y squared equals 1, it means that coordinate point is exactly 1 unit away. In other words, it's all the points inside this circle, right? The interior of this circle. Okay. So what are the boundary points of this? Well, the boundary points, they're what we think they are, right? So for instance, let's start with what's not the boundary point. If I draw any point in this circle, I can draw a disk around it where all the points in that disk are part of the set, right? Every point in this circle is in the interior of our set. Let's call this set, let's call it S. So actually, let me use better notation here. We can do better than this. We should be using this more often. So let's let S be the set points x, y such that x squared plus y squared is less than 1, okay? So now, if I draw any point in what we intuitively think of as the interior, right, you can imagine drawing a circle around it that's within the larger circle, within S, right? And it doesn't matter how close to the boundary I get, right? I can always just draw a tiny, tiny circle away, right? So if I'm not on that dashed line, it must be some distance away from that dashed line, and I could draw a circle half the distance away, and then every point will be within, right? So no matter how close I get to that line, if I draw a point near it, I can always draw a circle inside there. And similarly, if I choose any point outside the circle, it's easy to draw a disk that doesn't contain points inside the circle. However, on the boundary, on this dashed line, any point on that line, if I draw a circle around it, no matter how small, is going to contain points inside and points outside. That's what makes it a boundary point, right? In this little blow up over here, try to draw a disk around a point on that boundary. That doesn't include points inside and outside of it. So that's what a boundary point is, right? It follows our intuition. So the set here that I've written does not contain its boundary points, right? We're not including those points on that dashed line, right? I've insisted that the point's distance be strictly less than. On the other hand, if I change this set and simply say less than or equal to 1, now the boundary is included in that, right? And so one common notation for this, similar to how on a number line, when we include the boundary, right, that's not including that part on the number line, and this is including whatever number that represents. We use dashed and solid lines often to represent whether or not we're including the boundary, right? So that's the difference between closed and open sets. Let's just do one more example. Let's take the set, I'll call it R, is equal to x, y, such that, let's say x and y are both positive, and y is less than or equal to 1 minus x, okay? So let's see if we can figure out what this point or this set looks like. So I'm going to start with a coordinate plane. Okay, since x and y are both positive, I know I'm in the first quadrant. I also know, well, let's do one thing first. Let's look at this y is less than or equal to 1 minus x. Let's think about equal to 1 minus x. I know that's a line that looks like, let's draw it in blue, something like this. Right? It's a line with a y-intercept of 1 and a slope of -1. So that's that line. So let's see if we can figure out from this picture exactly what this set is. So first of all, I need values greater than x, values of x and y that are positive. So I'm in this first quadrant. Less than or equal to this line means on this line, y and x are equal. Well, I need y to be less than or equal to. So that means I should be including this line. So I'm drawing a solid line there. And points below it. I can't move beyond the y-axis to the left or beyond the x-axis below because then I'm no longer positive. I'm also not including points where x and y are 0. In other words, I'm not including these axes. So this set is the interior of this triangle. It includes the hypotenuse, but does not include the legs. So this set here is not a closed set, right? While it does contain some of its boundary points, right? The points along this line would be boundary points because if we draw a circle, they contain points in and out, but it's not including these boundary points. And so to be closed, you have to include all of them, right? Even if you're just missing one, for instance, if we took this circle here and said all of these points, but also except, let's say 0, 1, right? Now I've got a hole right here. That's one of my boundary points. So it includes the infinite number of boundary points except for this one. It would now be not closed anymore. So we will need closed sets for the theorem we're going to talk about next. We need one other thing. Besides being closed, we need our sets to be bounded, right? And bounded just means contained within some disk, right? In other words, you can draw a circle around it, right? Now, it might feel a lot like closed sets have to be bounded. We're containing, it's like they feel very contained, right? Contained within some disk just means, again, you can draw some circle around it, so it's finite. It's not going on forever. Just to give you an example, here's a closed set that's not bounded. I could have a set, I'll call it A. It's going to be, let's say, we'll make it easy on myself. Let's say it's all the points x, y, such that x is between 0 and 1, and y is between, let me make sure I get this right. Let's just say something like 2n and 2n plus 1, where n is an integer. All right. So what does this thing look like? Well, x has to be between 0 and 1. Let's include 0 in our integers. Actually, let's make this simpler. Sorry, we'll make it the natural numbers. That's what I meant, actually, which is why I said let's include 0. So let's make it the natural numbers. Some people include 0, some people don't. For the purposes of this, I will. So now x, when n equals 0, our first integer, we're going to go from 0 to 0 plus 1. So we'll have this box. Then for the next integer, which will be 1, we'll go from 2 to 3. We'll have this box. So notice in these boxes, x is always between 0 and 1. And we're taking these boxes that start at the even numbers and end at the odd ones. It's skipping the parts where we start at the odd number and end at an even number. So you get this series of boxes that's going to go on forever. We're definitely going to include all of our endpoint or boundary points because these are the boundary points, the outlines of these boxes, and we included all of them. But I can't draw a circle around this interval because any circle I draw, any disk I draw, there's going to be some boxes outside of it because it extends infinitely as we go up this range. So we're not going to dive deep into these kind of, you know, odd sets that we don't really have to worry about in most of our simple applications. But it's sometimes helpful, I think, to see a counterexample for a seemingly simple idea that isn't necessarily true. I know it seems sort of like closed and bounded almost feel like very related to each other, and they are in some sense, but you can certainly be closed and not be bounded, and vice versa. Okay, so let's now, with these ideas in hand, let's make the following statement. This is our version of the closed interval method, our version of something we did in single variable calculus. We will say that if f is continuous on a closed, bounded interval, sorry, not interval, excuse me, that's the, from single variable, on a closed, bounded set, we'll call D in the xy plane in R2, then f attains an absolute maximum and absolute minimum on D. Let's say maybe at some point in D. Okay. So what is this? Let's look at the picture first, right? I might have some function. This is a bit harder to draw. Let's say I have a function like this, right? That maybe. So what I'm trying to draw here is a surface that, right, just like when I draw a line, but I have to end it. Imagine the surface extends forever down to infinity, like points just keep going lower and lower, and maybe this ends going higher and higher and higher. But in the middle, it might have some bumps and some points, some ridges and things on it, right? So if the xy plane is down here, if I pick a closed interval or closed set, right, and look at the points, the values of the function simply on this set, right? So I can imagine just drawing the projection of this set up to the surface, right? In this region, I guess it's closed, so I'm going to include the endpoint. It must have a highest point and a lowest point, right? So maybe this point here, maybe there's a dip in the middle that's the lowest point, and the point on this ridge over there, right? So we're only looking at a portion of our function. It's exactly the same as in one variable calculus when you have something like this, right? Some function that doesn't have an absolute maximum and minimum because it's going off towards infinity in both directions. If you then take a closed interval, let's say from here to here, this piece of it has an absolute minimum on the endpoint and an absolute maximum at that critical point over there, okay? And we use a very similar process to find it. We find the critical points in D and evaluate, right? Meaning find the value of f at those points. Find the extreme values on extreme values, let's say, of f on the boundary. Compare, right? That's what we do. Just like the method on a closed interval is, you find all the critical values and evaluate the function. You evaluate it on the endpoints, and then you compare, okay? Now, finding the extreme values on the boundary turns out to be its own little problem. But what happens is on the boundary, right? Even though this looks like an odd, curve floating in space, we can often reduce it to a problem of single variable calculus, okay? So I'm going to illustrate that with an example here. So let's take a look at the following. So now we're going to go to a nicer graph. Let's do this. All right. So here's a function. Second. So this function that we're looking at here, oh shoot, oops, 1 second. Thanks. All right, there we go. I need to annotate. Okay, the function we're looking at here, f of xy, is, let's see, x squared plus 2x plus y squared. Let's find the absolute max and min on the set x squared plus y squared is less than or equal to 1. So this is our set D. Let me write it nicer again. On the set D equal to the points x, y, such that x squared plus y squared is less than or equal to 1, okay? So looking at our picture here, right, it's pretty clear this function has an absolute minimum anyways, right? I mean, we can do some work to show this, but just looking at this picture, if ignoring the closed bounded set that we're looking at here, it looks like it has a minimum anyways. The problem is it doesn't have an absolute maximum everywhere. So what is this problem asking us to do? Well, first of all, we're looking at the set of points x squared plus y squared is less than or equal to 1, right? So that circle now, it's a unit circle around the origin. I've drawn into the origin, around the origin there. So all the points on that circle and in its interior, we want to know where does this function achieve its maximum minimum on those set of points, on those set of inputs. Right? So let's picture this. If I extend that set of points into the z direction, right, you can see where that surface, where these two surfaces intersect, inside of there, right, is the points we're talking about. In other words, let's get rid of this now. Let's get rid of this. We're just looking at, so it's not rendering great. Let's get rid of the function. Here is just the piece of the function that was inside, right? So here again, here's the whole function. If I take the whole function away, I'm left with just the piece that was inside that tube. And remember, that tube was just showing us what's above, right? The part of the function above and below the set of points in the domain we cared about, right? So from above, these shapes match up. So we're just looking at the surface for the domain we care about. And this is our closed bounded set, right? I can certainly draw a disk around that. It includes all of its endpoints. So we want to find the absolute max and absolute minimum of this function on this interval, on this closed bounded set, okay? So what was our method? Well, first we find the critical points, right? The critical points are where the x and y derivatives are 0 at the same time, right? So let's look at our derivative with respect to x. We get 2x plus 2. And let's see where this thing is equal to 0. 2x plus 2 equals 0 when this is simple enough, when x equals -1. Let's look at the partial with respect to y. This is just going to be 2y, and 2y equals 0, again, simple enough, when y equals 0. So the only critical point is at -1, 0. Right? They have to both be 0, right? There are lots of points where the x derivative is 0. For instance, -1, 1, -1, 2, -1, 3. The x derivative, or partial derivative, is 0. But at those points, y isn't, and vice versa. Again, any point on this surface whose y coordinate is 0 is going to have a partial in the direction of y, a partial derivative with respect to y of 0. But we need them both to be 0 at the same time. So we don't need to do the second derivative test. All we have to do is evaluate the function at this point. So f of -1, 0 is equal to -1 squared plus 2 times -1 plus 0 squared. So f of -1, 0, we get 1 minus 2 is -1. Okay, so I'm boxing that. I don't know what answer that is yet, if it's an answer at all, right? I'm just going to go through the whole process. You might guess from this picture what's happening, but either way, all I have to do is evaluate at the critical points. In this case, there's one of them. And then I'm going to take a look at what's happening on the boundary, okay? Now, here's where things get a little more interesting. Remember what we have. Here's our surface. I'm going to use z this time. X squared plus 2x plus y squared. The boundary is all going to be the points where x squared plus y squared equals 1, right? That's the boundary of this domain. So if we go above, right, remember we were looking at, here was our domain. The portion of the domain we cared about is this little circle in the xy plane, and we find the points on our surface above or below. In other words, we evaluate each of those points, and that creates the boundary of the portion of the surface we're looking at. Well, all the points on this cylinder have, because they're on this cylinder, means that their x and y coordinates, the sum of the x and y coordinates squared is equal to 1, right? In other words, on the boundary, I can take this equation, and if I wanted to evaluate z just on the boundary, because at the boundary this is true, x squared plus y squared is 1, then it's easier to evaluate z on the boundary by saying, well, I already know x squared plus y squared is 1, I just have to add 2x. So every point on this boundary is equal to x squared plus 2x plus y squared, but on the boundary, x squared plus y squared is 1, which means we can evaluate on the boundary as 1 plus 2x, and that will give us the same points. Okay? Now, the other thing that's true on the boundary, and this is obvious from x squared plus y squared is equal to 1, that x has to be between -1 and 1. So the boundary includes only x values between -1 and 1. And z on the boundary is 1 plus 2x. Okay, let's rotate this picture a little bit. So here I am looking straight, looking straight down, more or less. Let's see if I can get a little better. So more or less, we're looking straight down the y-axis, right? Notice this equation now doesn't include y. We can evaluate z simply by looking at x along the boundary. The boundary, let's use, is this edge here. Here, let's use a better color. Sorry. Let's use, let's try orange and see how that works. All right. So the boundary, right, from this perspective follows this line. Right? And if you notice, that line is precisely z equals 1 plus 2x. Right? Now, if I rotate, we know that boundary is actually a circle, but we're eliminated all the y information, so we're kind of ignoring the back and forth of the circle. There's kind of these two sides go up following this, z equals 1 plus 2x. We could also think of it as a plane. If you took a plane, if we took this plane, z equals 1 plus 2x. In fact, let's do that for a second. Let's plug that into this. Oops, stop annotating. Z equals 1 plus 2x, right? We see that plane, right, is living right on the boundary there. And we can see that it looks exactly like the line z equals 1 plus 2x if we were just dealing with z and x and had no y dimension, okay? So now all we have to do is find what are the extreme values of z equals 1 plus 2x over the interval -1 to 1. And that is a fairly simple problem, right? You can use calculus and see that it's an increasing function. You can just use what you already know. This is because it's got a positive slope. It's going to be at its minimum at -1 and it's positive at 1. So our extreme values are at x equals -1 and x equals 1. Okay, so at x equals -1, y equals 0, right? You can use this equation, x squared plus y squared equals 1, because remember these points are on the boundary. So if x is -1, we get 1 squared plus y squared equals 1, so y equals 0. Same at x equals 1. Y has to be equal to 0. Well, it looks like this extreme value on the boundary is the same as the critical point. So one of our critical points was at the boundary, right? So we've already taken care of that one. So now let's look at the point x equals 1, y equals 0, f of 1, 0. Now I'm plugging back into the original equation. I get 1 plus 1 squared plus 2 times 1 plus 0 squared gives me 1 plus 2, or 3. And so what we're finding in the end is that the absolute max and minimum are the bottom of this, right? This point down at the bottom of this little shell and the top of this little shell, right? Which is pretty obvious from the picture, but it might not be exactly obvious which point it is. And we've shown that these are the absolute maximum and absolute minimum. So we have a fairly simple routine on a closed interval. As long as if you have a closed bounded interval for your domain, you have to have an absolute max and absolute min if your function is continuous, right? This was a pretty clearly continuous function, just a polynomial. To find it, you simply find the critical values. That's usually straightforward. Solving for, you compute the partial derivatives with respect to x and the partial with respect to y. Find out where they're both equal to 0. Sometimes there's a little bit of a system of equations involved. We did something like that in the previous video. Then you have to look on the boundary, and that can sometimes be tricky. This is probably on the easier side. I'll do some examples moving forward that might get a bit trickier, but they usually reduce to a problem of a single variable, right? We end up with this function, z equals 1 plus 2x, right? That's what we ended up with when we looked just at the boundary, right? And so when we turn into a function of a single variable, we know how to find those max and mins. This one we use basic pre-calculus stuff, basic algebra stuff. You could also use calculus, right? If this had been something like 2x squared, we know how to find max and mins of functions like that. You go back to Calc 1 and think about how you did it there, okay? All right, that's gonna be it for this video. Thanks everybody. I will see you in the next one.